Hello everyone, welcome to the day 5 in your LLM mastery course in 30 days. In this video, we are going to see about the different types of position encoding, including absolute position encoding, the types of absolute position encoding, relative position encoding, what are the methods in which you can do the relative position encoding, rope, and then we'll also see mixture of position encoding, how you can add two kinds of position encoding for your own custom use cases. And then we'll also see one of the latest methods, which is ALiBi. And in each type, we'll see anything and everything which you need to know about the each type. For example, we'll see about what is a type all about, the mathematical formulation of it, why should you use that type, how it works, a detailed code implementation for the type, and also we'll see a plot on how this positional encoding will impact the model's attention. We'll see those as well, and then we'll see the pros and cons and how it is compared, or how it is pairing against all the other methods. So you can see that this is going to be a very comprehensive video, so stay till the end and have a good learning ahead in this video. Let's start with absolute position encoding. What is absolute position encoding? It is a method in which you'll incorporate position information to the transformer model by assigning a very unique vector. It will, for example, position 1 will have a unique vector and position 2 will have a unique vector, right? But this position in encoding, right, this will not change. It will be always the same. If I run it even after 10 times, it is going to be the same. Okay, always the number 10 will have, let's say, a vector starting with the number 0.5. It will be always 0.5. Okay, so this will allow the model to distinguish between the tokens based on the absolute position within the input. Because we all know why position encoding is important. It will try to provide the position information to the token because of one of the examples which I have discussed in the transformers video itself. But I'll again provide you with that. I love eating apple at Apple Incorporation, right? Here, incorporation, the position of incorporation is what providing context to Apple that, that is a company, and eating is what is influencing Apple as a fruit, right? So for that, position encoding is important, and we can do that even with absolute position encoding. What are the types in which you can do absolute position encoding? First, the position encoding method which was there in transformer paper, which is sinusoidal encoding, where you'll use a sine and cosine wave. For even positions, you'll use sine wave, sine of position by 10,000 to I by d model. I here says about the ith embedding dimension, and if it is odd, you'll use cosine. Okay. What are the pros for these methods? It is deterministic, which means it is not going to change. Like I said, it is a mathematical formula, so it is never going to change. So you need not learn for this. And also, to some extent, it can extrapolate to unseen sequence length. For example, you have trained it only for 1024. Okay, since it is just a mathematical equation, right? If I give 1025, there is going to be still some value to it, but you can't expect good results. Okay, that is there. And the values are within a bounded range. It is between -1 to 1. So that is also an advantage. Cons is that, since you have a fixed pattern, there might be data which will have flexible pattern being required. So in that case, this might fail. So since it is not flexible, it cannot capture complex positional relationships and all. So that is sinusoidal encoding. And in learned position embeddings, what we'll do is this is a method which will involve using a unique embedding for each position. Like the most famous method of absolute position encoding is this learned position embedding, because this method is even used nowadays. Okay. If you see in PyTorch, there will be a layer known as embedding layer. If you use that, that is a learn position embedding. Okay, for each position there will be a vector which will be calculated. Okay, and that vector will remain the same when we start. Okay, but when you do for training, right, it can train itself and adapt itself for data specific things. But how it is going to be absolute here? You see, like I said, for each position, there is always going to be a value in a table, right? So it becomes absolute here. There is nothing, relative to one token. So if there is an impact of one token onto another, then it becomes relative, right? The position becomes relative here. But here, regardless of what, like how many numbers are there, it doesn't matter. This token has its own position value. That's all. Okay, so given a position, I'll see my lookup table of embedding, and that is a learned embedding table. While I'm training, it will be trained, and there I'll get a value. Here we'll overcome one of the issues which was in the cons here, which is it can adapt to data specific patterns because you're training it, and it is simpler to implement. Here also, and here at least you need to code those, okay? But with learn position embedding, you can just call n.embedding and that will be more than enough. But since you call n.embedding, right? Imagine that as a table. I have a table of values from 1 to 1024. What if I have a value known as 1025? Can I have an embedding for that? No, right? You don't have some values in the lookup table, which means there is no way you can extend the maximum sequence length. If you train it for 1024, it can only work for 1024. That is an issue with learned position embeddings. And it also requires additional parameters to learn because embedding layers are learnable layers. So it increases the parameter in which you want to learn. But learn position embeddings are a very good method when you want to encode things like, for example, your VIT models, right? In vision transformers, you'll have patches, image patches. To encode the position of those image patches in which order the images was there, at that time, you'll require learn position embeddings. Okay, these methods are very useful. And there are two unpopular methods, not good in any way probably. One is algebraic encoding, where you will not even use sinusoidal, but it is going to be same, where what you will do is position by what is your max sequence length, and will subtract 1 out of it, and then power of 1 by d model minus 1. That is the equation here. It uses an algebraic formation, but the thing which you need to note is you can also make something like this. What if you want to make something like max sequence length by 2 or so? That is also something which you can try to do, and if you do that, you need to divide the position values also by 2. Okay, that is also there, but that is the beauty of math. You can customize it however you want. So here the pros are that it is deterministic, and since it is again a mathematical formula, it can handle arbitrary sequence length. But the cons remains the same as in the sinusoidal encoding. It can't capture complex positional relationship, and it is not adaptable at all. Probably the worst method is bit, where each position will be represented with binary representation. For ith bit, there will be a binary representation of the position. Okay, so it will be compact, deterministic, and you are just going to give a binary value for each position, so it can handle long sequences. But cons is that it is very discontinuous in nature, and binary encoding usually takes some processing, so that is also a concern. But these are the types. But you need to more know about learn position embedding and sinusoidal encoding. Sinusoidal encoding we have discussed in detail already. Learn position embedding, like I said, it is just n.embedding. That's all. Okay. So why should you use this absolute position embedding? Any of these type. First, it is unique. For each position, it will give a unique value. It is fixed, which means the encoding is deterministic, and it doesn't require any learning unless until you use learn position embedding. Okay, and then there is boundedness. Always the values can be scaled because you are controlling this. It is all mathematical except n.embedding. All are mathematical, which means you can bound it between whatever you want, whatever value you want. And some can generalize to sequences longer than those what it has seen during training. And if you have embedding layers, you can pre-compute it and store it as PT file or something like that, so that you can have a quick lookup. So it is very efficient in nature as well. So those are the advantages of absolute position embedding. So how it works? First, what you will do is you will generate unique vector for each position using any functions, for example, sinusoidal function, and then you will add the position encoding to token embedding, and then you will send it to the model, and the model, which is attention, basically will use this information while training. This is how absolute encoding will work while transformer training. And this is the code. We'll go through the code later because code I have written it in a better way as well. This is to keep this specific document cleaner. I have added doc strings and comments, everything which is required. All of those are done, and those are in a separate file. We'll see that later. Okay, but on a general level, if you see, we'll compute the positional encoding and then we'll use it in attention. This will be common for every type. That is how we'll understand how positional encoding basically works. What are the pros? And pros are mostly the reasons why you should use positional encoding: simplistic, deterministic, extrapolation, efficiency, stability. All of those are there. And cons are that it is fixed, it is limited, it can't capture complex relationships, no relative information. So one position doesn't affect the other. But for example, the apple at position 1 and apple at position near incorporation should be given different values with respect to incorporation, right? Or good. So that relative information is missing here. And also it is very highly sensitive, because if you change the dimension, everything will be changed, because everything is mathematical. So it is hyperparameter sensitivity is high. And now if you compare with other methods, learn position embeddings require for you to learn, but other methods in absolute encoding can't learn, which means that is an advantage or else disadvantage, depends on the use case. And then there is relative position encoding, which will encode relationships between position, but absolute encoding can't. But absolute encoding can provide unique representation for each position, which relative position encoding can't. Rope is more effective in capturing relative information, but absolute encoding is more simpler. And a similar thing will be applicable to ALiBi. Why? Because ALiBi is a relative position embedding kind of a method, so it can scale with very long sequences easily. But ALiBi is absolute is simpler, but can't scale a lot. So yeah, that is about absolute position encoding. And if you are wondering, okay, where is the code? Code, like I said, will be covered once all the types theory are covered, because the codes alone will have a lot of information in it. Theoretical is different and practical implementation is different. So we'll see that later. Next, we'll see about relative position encoding. So basically, this is how relative position encoding will look like. If I have a token here, right? Absolute position, what it will say is it is 0, 1, 2, 3, 4, 5, 6. So 6 will have some value to it, and that is the value which we'll use. But when we use relative, it will give information on how many tokens were before that, how many tokens are after that. So all of these positions will impact the position of this cook. Okay, that is how a relative position encoding would work and should work. So relative position encoding, if you see, is a method of incorporating positional information into transformer model by encoding the relative distances between the tokens rather than the absolute position themselves. The name suggests itself. So this approach will allow the model to focus on the relationship between the tokens. Please highlight this. Okay, it will give more importance to the relationships which is existing between the tokens. And that will be very useful for the task which depends on local context. I told you, right? The context. Apple incorporation. Here the incorporation is giving context that it is a place or a company or whatever it is. So wherever there is a requirement for context, relative position encoding is a better option. So mathematically there are two methods. One is Shaw et al. So that was for a music transformer, where what they would do is they'll have learned weight matrices WK, WK, E, R. Okay, and then there is WQ. Q is weight matrices, K is key matrices, E and R are the starting and ending position. Okay, so here is a formula where you can just assume that X is your query. So query I will be multiplied with WQ transpose and then WEK xj, like the tokens at position j, that value will be there, right? Usually we'll provide x as q and k and all, so that's why I said q or k. If you're considering as tokens, that is very good. And token embeddings, just consider as token embeddings for now. The token embedding of ith token is multiplied with weight q transpose, weight q and made transpose, and then what we're doing is weight ek is computed on xj, and then this value will be added with WQXI transpose plus WKR and relative position distance. Okay, it is a learned embedding. Here you can see for the relative position, clip to a maximum absolute value. It is a learned embedding value. So it is, providing some scalar value which you can scale and say like, this is how the intensity of distances. So this is not a method which is more commonly used. The more commonly used method nowadays is transformer XL method, and that is a method which is used in models like transformer XL, T5 and so on and so forth, where what you will do is you will compute the sinusoidal embedding, but that sinusoidal embedding is now made as a relative embedding, where instead of computing it for a position, you will compute it for the distance itself. Okay, the relative positions will be encoded here. If you see the formula seems similar, right? Position by 10,000 power 2i by d. Okay, but here we are computing for example 10 minus 8, which will be 2 by 10,000 power k, the current position, by d. That is how the position encoding is calculated. And here what we do is we'll be adding those with some learned vectors. Okay, and the formula, if you see, these are similar. Okay, here if you see, we have a normal value, but here what we'll do is we'll add a learned vector to it. So similarly, we'll also add a learned vector to here. Instead of using a learned weight matrix for the multiplication with the learned position embedding, the distance, we'll be using a mathematical formula there. That is what is the difference between these two equations. Don't worry, theoretically it will sound very hard. Most of the position encoding methods will look like that, but once you see the code, right, you'll understand, okay, this is easy, something like that. So you can see we are more emphasizing on I minus j, right? The distance between two tokens, that is the emphasis here. So that is what is the first reason you need to use relative position encoding. It emphasizes on the relationship between the tokens rather than the absolute position. And then it will handle long range dependencies easily, because rather than using a number, you'll use the distance between tokens. All right, so it is easily more scalable for long range dependencies. It can extrapolate easily, and then it is also efficient in some way. How it will work? So basically you will first calculate the relative distances between all the pair of tokens. So 1 with respect to 2, 1 with respect to 3, 1 with respect to 4, like that. And then for those you will generate the encodings, either learning or mathematical function. So this is a learning method. This is more of a mathematical function method. So you'll use any of those methods, and once you compute those embeddings, it will be provided to the attention, and those attention now will utilize this relative positional information to learn the relationships between the tokens, and it will have a better training. That is how relative attention works. And here you can see this is a relative global attention, which is almost the same implementation of transformer XL method. And don't worry, we'll come to this later. Okay, and pros we have already seen, as well as the cons. If you see, it is very computationally intensive for long sequences, right? So imagine I have 1024, so I'll have 512 plus 512 minus if I am in the center, right? So that is computationally a bit complex. And then since you are involving a lot of relative position, it will become more complex to implement than absolute position encoding. Even I faced a lot of errors when I was writing the code. So the absolute position information, which may be suitable for some tasks, you'll lose in those tasks. Okay. and then the memory usage will be very high for long sequences, and it is also hyperparameter sensitive when you want to consider the maximum relative distance. So how much maximum relative distance you are considering is a very important hyperparameter, and that can decide a lot of things in your performance. So this method also can be said as a hyperparameter sensitive method to some extent. So what are the comparison to other methods? So in absolute position encoding, you will encode the absolute position, which can be beneficial for many tasks, but at some time you'll require those kind of embeddings, like I said. But relative will focus on the token relationships, which is useful for many tasks, but at some point of time you will lose the global position information because, like I said, the maximum relative distance is a hyperparameter and you can't keep it 1024 or 2048 and all, and because at runtime it will become very hard for you to work with. So that is something you need to think of. And sinusoidal, like I said, can be extended, but it can't capture complex position relationship, but RP can, and it is also more flexible because it is just working with relative distances. Rope, but it is also similar to relative. Rope and RP both are relative positions embedding, but RP will use relative position embedding will use separate embeddings, but rope, what it will do is it will try to integrate the information directly into the token representation itself. Okay, so here you can see, right, there are separate embeddings here, but rope is about if you want to transform embedding separately. Let me simply explain. Okay, so RP, if you see, has separate embeddings. Even rope has a separate calculation that is there. But with rope, what you'll do is you'll rotate the initial tensor directly. You'll directly impact the rope information, which is positional information, on the token representation itself, the vector itself. But here you'll have a separate position embedding, which you will add later. Okay, that is how rope and RP differs, but architecturally rope is superior actually. Okay, and that is what we are going to see next, which is rope. So the idea is that if you see with other methods, if you encode it right, for position 1 the value will be here, position 2 the value will be here, position 3 the value will be here, position 4 the value will be here, like this. Okay, there is not a pattern in which it can understand, right? Because the relative information will always provide different values, but with rope it works more on the angle. Like the distance between two vectors is calculated as an angle, and with that angle it is just rotated. Okay, the vector will be rotated at different position, and here you can see, right, if the position is this, it will be the starting position is this and ending position is this. For m is equal to 0, it will become m is equal to 1, m is equal to 2, m is equal to 3. I can see a circle kind of structure, so it is more simpler, and it is easier for the model to understand things which are going behind in rope. So since it is very simpler, it is also computationally efficient. Now let's see about rope. Okay, for all the theory, just have all of those in mind, because these are just to provide you the context. Okay, once you go to the code, you will understand how these works. Rope, if you see, is a method for incorporation of positional information in transformer model, where what you'll do is you'll use rotation matrices on top of the token embeddings. Okay, so here rope, what it was created, why it was created is absolute position encoding were very good with capturing the absolute information, and also it were very good with computationally being efficient. But relative position encoding were having a relative distance, but were highly computationally intensive. Okay, so it tried to find the bridge between those. That is how rope came. So what they will do is, first each value will be considered as a complex number, as a vector, where what they'll do is they'll do a rotation operation. Okay, so the rotation angle, right, this angle will be known as theta. Okay, and theta will be equal to wi power minus k. with W and K being hyperparameters. You can define at what rate of angle you want to turn. You can do that. And here the M which is there, right? M is position index. Okay, I is embedding index. That is what is in here. Practically how rotation will happen is x of 2i minus 1, which is the embedding at 2i minus 1 of x, it will be rotated with cos m theta I, and minus x 2i. Similarly, this thing will happen. How this equation came is, you will apply this x2i minus 1 and x2i on top of this rotation matrix. Okay, if you calculate it, this will work. Okay, that is how it works. I hope you got that. Now, in attention, what we will do is we'll use this rotation matrix computed information on top of query and key to be multiplied before computing the query key transpose. Okay, basically this rotation matrix is gonna provide me the positional information with this rotation, and that is applied on top of query and key directly, and yeah, that is gonna provide me all the information which is required. Okay, so that is why I said it works on the token embeddings directly. There is no separate position embedding for rope. Okay, so why you should use rope? It is finding both absolute and relative encoding, because when you are working with one token to another token, right, this is the starting token and this is the ending token, the distance. Okay, so always this absolute encoding is also there, and you're trying to find the relative information with some angle. Okay, so both of those information are still there, so that is why it is finding a bridge between absolute and relative. It is flexible. It also preserves linear self-attention properties. It is efficient, and it is good at extrapolation. This is probably the best method we have discussed till now for extrapolation. It can extend even up to 16 times is what I have heard till now. Let's say I have trained it for 2000 tokens. It can be extended up to at least 128k or even more. That is what I'm hearing, but I'm not sure. Okay, I have not worked with rope personally, so I'm not sure of that. But it is also very efficient because it is just simple matrix operation, right? You are just having a rotation matrix, you're applying that. That's all. Okay, the calculation of rotation matrix is there. You need to rotate your tensor in half, split it. Those are different, which we'll see while coding. Like I said, theoretically it will look different, but practically it will look very, very different. We'll see those. But it is very simple to implement, and it is computationally more efficient because it is just simple matrix operation. First, what you will do is you will generate a rotation matrix based on the position, and you will basically rotate your query and key tensor or vectors with this rotation matrix, and then you will compute your attention. That is how rope will impact while training. Here is a sample implementation. Again, we are not going to go inside. We'll see that in the coding section. The advantages are, again, unified encoding, efficiency, extrapolation. Theoretically, it is better, and also it is very flexible in nature. The cons is that it is a bit more complex to understand, not to implement. Implementation, I'll say it is not as tough as there are some other methods. But still, comparatively to absolute encoding and all, this is a more complex implementation and complex to understand concept. It is hyperparameter sensitive on the choice of base frequency. Base frequency is what is the theta going to be defined on, and then you have how basically this position encoding is rotated. You don't have a lot of idea in that, because in other methods you can print the embedding, you can somehow see the embeddings, but here how these embeddings are going to impact, you can just see with the help of attention. So interpretability is a bit harder, and also other than that, you have numerical issues, because with very long sequences, again, the rotation angle might not be enough, and that can be a bit hard. Okay, I'm thinking of making a separate video on rope, because or else even when we implement an LLM from scratch, which I'm planning in future, we'll be using rope only. At that time, I'll be even more explaining about the theoretical aspects. Okay, because at that time you'll require this. And then now we have another method, which is mixture position encoding. Mixture position encoding, as the name suggests, it is to combine multiple position methods so that you can get the advantages from both. For example, absolute position encoding will provide unique representation. Relative position encoding will provide relationship between two positions. You can just add the information from these both, where what you need to do is just have an alpha parameter, which is a learnable parameter. Okay. Or else you can also have it as a fixed parameter, that is also fine, like a scalar value, and this will decide how much value should be provided for absolute information and how much value should be provided for relative information. If you keep both of those same, or both of those will be like in equal composition. But if you want to provide some weightage more for relative because the task demands that, you can provide more for relative. Okay. And here what you can do is you can just use absolute and relative position encoding, like I said, and the advantages and disadvantages are gonna be not a lot actually. So if you see the advantages, it will capture both information, which means it is very flexible. It will have a better performance than the single one itself. It will generalize more for short and long sequences, because with the absolute encoding it will work very well for short sequences, and with relative position encoding you can handle long sequences very effectively. So it will be more generalized, and it is adaptable for many tasks because it is adaptable for short and long sequences. So how this will work is, first you will calculate the absolute position encoding, and then you will create a relative position encoding for each of those positions. You will add those with the mixture parameter or the alpha parameter here, and then you will compute the attention. That is how it works. And the pros we have seen already. The cons is that it is going to be more complex than how it was before. The computational overhead is high because like you are adding another component. If it is relative, you are adding an absolute component. If it is absolute, you are working with the relative component, which is more computation, right? So unless and until an absolute position embedding related task requires a relative component, don't use that. And here it is the hyperparameter sensitivity is still there. Every method has its own hyperparameter sensitivity, and here it is the mixture parameter. Okay, how much should I provide weightage for each of those methods? That is very important. And then the conflicts might occur, like absolute information will provide importance to something, and relative will say that is not important, another thing is important. So that conflicts room is there for that. And memory will be high, okay, because you need to store at runtime. Both of this encoding needs to be stored. So that is about mixture. Mixture is not very complicated because now you know how relative works and absolute works. It is just adding both of those. Okay, last but not the least, and probably one of the most simplest method to do relative position encoding, and that is attention with linear biases. Okay, so in short it is known as ALiBi, where what you will do is you will actually have this kind of a matrix being generated for your attention. This ALiBi only works for decoder only model. Okay, so here in transformer model you will just involve this, and unlike the traditional methods, this is very simple, but it is very effective because it can handle long sequences. It can generalize to unseen sequence lengths, but it is very simple. Why it is that? If you see, the formula of attention becomes something like this: qk transpose by root of dk. It is same, but you'll add another component of m, which is a head specific slope. For each head you'll have a different m value, and that is a slope value. Okay, and here it is just a matrix of relative position. Okay, what are the position in the sequence, like what is the window you are going to cover, and then you'll just multiply it with v. That's all. And the slope you'll calculate it in this way. Okay, m of head will be 1 by 2 power 8 by number of heads, okay, into h minus 1. That is how the slope is calculated here. So from 0 it will be there till 8 or 16 or whatever it is. You can print the number of heads. So you can see, probably this has been the shortest time I have explained an embedding, right? It is very simple. Here you can see, you can just generate a matrix like this, because this shows the relative, right? 0 till here it is minus 4, the distance. You will multiply it with the scalar value m, which is the slope, and this will be added with the attention you already computed. This is the causal attention, which happens in the decoder, right? When you add this, the positional information is automatically impacted on the attention. Okay. So it is very simple, efficient, can extrapolate a lot. It is highly performing, and it also doesn't require a lot of memory efficiency because it is not storing. It is just computing at runtime, so it is not storing, right? So here ALiBi works differently. Okay, first you will calculate the attention score, and then you will calculate like the linear bias term here, which is m of I minus j, and then you will add that. Okay, you will add that to the attention score, and then you will apply the softmax, you will multiply the value, and that will provide you the attention output, right? So this is a bit different. The other methods, first you will compute the position embedding, and then you will compute for attention. Here, first you will compute the attention score, not the attention output. Okay, attention score, and then you will add the linear bias term. Okay, also coding is very simple for this. Okay, here you can see this is all it is required. Okay, it is very simple to implement ALiBi. So that also it's a pro. It is very simple, efficient. It can extrapolate because it is relative. Mostly relative embeddings can extrapolate. Okay, it is highly performing algorithm. It is very memory efficient. It is also very interpretable because when it is a linear relationship, right, you can clearly interpret it. For example, if I give it as -5, I know it is going to be something like this. And if I have m value, which is going to be a mathematical value, I know what is the value which is going to be here, and I can calculate what is going to be the whole values in here. And then if I add this, and if I know this output, I can easily subtract this to know what happened in here. So it is more interpretable. Okay. And here, the cons is that it is fixed. The linear bias is fixed. So it might provide you limited flexibility. It is task sensitive, wherever it requires relative embedding, that is where you can use this. Okay. And here the slope calculation formula, it is said in some places that it is required to adjust. This is one of the formula, but you can calculate it in any way, but it should involve the number of hits. Okay. And as far as the comparison is concerned, ALiBi doesn't require explicit position encodings, and also it can generalize to longer sequences. Like I said, it is not storing anything, right? So that is again an advantage against relative position encoding, because ALiBi is simpler, it is memory efficient, but with relative position encoding you may capture more complex relationship, but it is not with the case with ALiBi. With rope, ALiBi is far less complex, to implement and understand and all. But rope will provide more positional information better. So these are the methods which are there. I hope you would have understood. I know these are a lot of information. Some might think that I just read. This content is written in such a way that it is very simpler to understand. Even if you don't understand the mathematical section, please try to understand the pros and cons, when you should use a method, how this method basically works. That is very important. And for how, what better way rather than going through the code itself? That is what we are going to do now. We are going to go through the code of each of these methods. So here are the codes. Here you can see absolute position embedding is there, relative position embedding is there, rotary is there, mixture position embedding is also there, and also ALiBi is there. ALiBi has been the shortest one and easiest to code. Okay, but we can go in the order in which we saw already. Okay, first we'll see absolute position embedding, and here you can see it is a multi-method class I've written here. So what happens in this init function is that we'll set up the different position encoding methods, and we'll store informations like model dimension, maximum sequence length. For regularization, a dropout layer is created, and the positional encoding method is initialized. Okay, so here you can see the parameters are dmodel, max sequence length, dropout, and what method you want. So all of those are added to self parameter with dropout all initialized as a layer. And then we are initializing the position embedding method, which method we want. If it is sinusoidal, I'll call the sinusoidal method. And if it is learned, I'll call the learned nn parameter. Like I said, nn embedding or nn parameter, both are almost similar. You can also use an nn embedding method. It will still work. Okay. algebraic method is there, where, like I said, you can just provide any math and that should be more than enough. And binary, so binary, what it will do is it will try to provide a value or 0 or 1 based on the position. Okay, so these are the methods. Now we'll go for each of those methods. Okay, sinusoidal method, if you all remember, first we'll initialize a 0 tensor. We already saw sinusoidal method in detail in the transformer video itself, so I'm not going to go in detail with sinusoidal encoding. Let me zoom it for you all a bit. So that would be the first step, and then what we'll do is we'll create a tensor of positions from 0 to max sequence length. And then what we'll do is we'll calculate the div term, right? That 10,000 part do I by d model, that is calculated here. And then we'll do that np.log minus np.log, right? 1 by 10,000 part di 2i by d model. So we have the division term now. We need to multiply those across the position, where for even numbers we'll use sine and for odd numbers we'll use cos. Okay, so that is what is happening at step 4 and 5. And at the 6th step, we'll just provide the position encoding with the batch dimension added at first. Okay, so that is how sinusoidal encoding works. And algebraic encoding, if you see, first we are again creating an initial tensor of zeros. Position tensor is created from 0 to max sequence length. And for each sequence, what we are doing is at each position, we are taking the position. Okay, and then we are taking the position value here, and for that value we are dividing it by the max sequence length. And then here, if you see, we are multiplying it by the position number by self.t model minus 1. Okay, this is the same value or the same code which we saw, the theoretical side as well, and that is written. Both of these are similar, but here we are using a sine and cosine kind of method. Here we are using a algebraic method. Okay, so that is why it is sinusoidal, and here it is algebraic. And if it is binary, we are just first initializing a 0 tensor position so that we can store the position encoding, and we are going through each of this position, and that position is converted into a binary position. Okay, so in those tensors, what we are filling is we are filling it with zeros and ones, and finally we're retaining those. Okay, so here you can see, so this is some place where we are going through each of those position, and then for each position we are just checking if it is greater than I, the position value. Okay, and if it is greater than 1, we'll just say that, like that is 1, something like that. So it is just zeros and ones. You can also do something like, even positions are 0 and odd positions are 1. That is also something which you can try, but it wouldn't convey any information. Okay, so in forward, what we'll do is basically we'll just compute. So here, if you notice, everything is PE. Okay, and here also in self.pe we are calling the method. Okay, so that we can have only one forward method. That is more than enough. So self.pe of is 2 comma extra size of 1, on top of this self.position embedding is applied, and then we are calling a dropout. So in attention, what happens is, first we are getting the batch size and sequence length. For a given input, we are computing the position encoding, and that is your x here. And what now you are doing is this x, which has the token embedding as well as the position encoding, is now, here you can see those are added here, right? X plus self.position encoding. Information is sent to the attention, which is a normal multi-head attention. Okay, so these are the values. And here, if you see, we are plotting some important plots. One is a heat map. Heat map is more important, and then there is a line plot as well. Okay, so let me show the plot, how it will look like. So guys, if you all like these kind of videos, see, just say me, you like these kind of videos, because I don't think anyone is making this kind of detailed video in YouTube. So yeah, please let me know if you like these kind of videos. It is getting ready, and here you can see in sinusoidal, if you see, the curves are there, right here you can see the curves are there. This is how a sinusoidal encoding will look like. And here you can see after a certain stage, right, everything becomes straight lines, right? So in embedding dimension till 300, it is giving some value. After that, it has become some straight lines. And here the encoding value of the position is provided. Okay, the encoding value of position 0 at dimension 0 is 0. Okay, so basically at dimension 0 everything is 0. Okay, but if I go to, for example, 153, which is the red one, here you can see at position 0 it is 1, at position 1 it gives a different value. This is how a sinusoidal curve will impact. Okay, I said you right, at each position it will give a different value at each embedding dimension. This is how it will look like. It is complex to see, but like that should convey the information. But here if you see the learned embedding, right, there is no pattern, I guess you can see in here, because like I said, that is just a parameter which is a learnable one which will learn itself. And here you can see again there is no pattern. Okay, in algebraic, if you see, we have computed our own, and that will always provide this kind of a output because the mathematical equation doesn't change. And here you can see for each position what is the encoding value which is obtained. This is not at all preferable because if you see the encoding value is becoming 0 to 100, probably you can add a scaling parameter later. And then finally there is binary embedding, zeros and ones. That's all. You can see either red or blue. No, so most simple method. And if you want to see in detail, right, there is zeros and ones here. So this is how basically it happens with absolute. Now we'll go for relative. Here is where things get tricky, right? Because absolute is very easy to understand. From relative it becomes a bit harder. Now we'll go through those methods which are relative in nature. Now let's start with the relative global attention, which is the most common method of relative embedding. Okay, here in initialization we are computing the dimensionality for each attention head. We are providing the linear layers. Also, we are providing a relational position embedding matrix. Okay, where there if you see, like we created something like torch.zeros of P, right? Here we are computing something known as ER, and that is the matrix which will provide the relative position embedding for each token with respect to the other token. And then we are also creating a causal mask, which is like for the triangular mask, which is to make sure the future is not seen. That okay. So here you can see linear projections, dropout layer, learnable relative position embedding of shape, max length to d head. So first it is initialized with a random normal distribution. It's not random. Okay, it's random normal. So it follows a Gaussian distribution. That is how it is initialized. So it is learnable, right? So it will adapt itself while it is training over time. Okay, so here in forward, what we'll do is first we'll get the input sequence, and then we'll reshape the key, query, value, and all in such a way that it is ready for calculation for attention and also calculation of relative position embedding. So the next step is to start computing the relative position embedding bias. Okay, so once that is done, first I'll explain the steps and then we'll go through the steps as code one by one. And then next we have calculation of attention score, where we will combine the standard query key dot product, which is QK transpose, which is normal, with the relation position bias, which is influenced by the self.er, which we created already. And then we'll apply causal masking, which is required, and then normal procedure. Okay, so how this will work? First, the sequence length should be not greater than max sequence length. Basically, these are just normal checks. First, what we are doing is we are making all of those ready, key, query, value, and all. And then we are finding the starting place, like where you want to start your relative embedding. From there till what is your sequence length, both are seen. Now, in the values of ER, we are just transposing it. Okay. So like I said, this is the position embedding information. Okay. For each number, there will be a value where it is. Yeah, you can see, right? Maximum length in which you want the relative attention to be. Like, for 1024 positions, we are computing the relative position. Okay. So if it is more than that, we'll not do that. Like, for 1024, let's say it is 1025. So we will do from 1 to 1025. Okay. So that is how it will work. So for that only, we are getting the ERT or relative position bias ready. So what we'll do is first we'll multiply that with query. Okay. And now we'll do an operation on a skew. Okay, skew. And this is an operation which will allow you to shift the bias matrix for relative position. We'll see how that works. Okay, so given an input matrix, you will do a left padding. Okay, like I said, what if there is a position which is, let's say, 1026. Okay, so at that time you need left padding. So left padding, and now you will just reshape the padded matrix into rows for each position. Okay, so that will give you batch size, number of heads, number of rows, and number of columns. Number of rows is nothing but the tokens, and number of columns is your embedding dimension here actually. Okay, you have reshaped it, and now you are ready, right? Because if that is before your position of choice, you are just making it 0. So those are done, and that is what happens in the skew operation here. Okay, and now you are multiplying with matrix multiplication, and then you are computing your attention, and you are filling your mask. Okay, basically this is what is happening. And if you see the attention, right, this will be very fun. This is one of my favorite attention output which we can see, because out of all the methods, this will provide you one of the best matrix to see. Okay, Python relative.py. Here you can see, right, how much each affects. Okay, future is already masked, so those are not even considered. And with past, here you can see, right? So you can see the previous ones usually have more score, and then like when you go even more previous, it will have a very, very less score, close to 0. Farther you go, closer to 0 it is, right? So it is query with respect to key. Okay, these are the query position, and this is a key position. With respect to each of those, we are seeing the attention. This is relative attention. Okay, now we'll see about rotary. Okay, and then we also have mixture. For mixture, if you see, we are not gonna do a lot hard things and all. What we'll do is we'll have an ended embedding, which is a relative embedding. First we'll compute maybe we'll complete the mixture embedding, and then we'll go for rotary, because mixture is more easier. So basically what we'll do is we'll create an absolute position embedding with the help of sinusoidal, and then we'll create an embedding layer for relative position embedding. And what we'll do is we'll also have an alpha parameter. Here it is learnable, because you're initializing it as parameter. So when it starts, it is at 50%, both are equal. But down the line it will adapt which should be given more information. So in forward, how it works is you will calculate the relative position embedding. You will also calculate the absolute position encoding. Both are calculated here. Okay, this is probably the most simplest method to calculate the relative position embedding. Okay, get the relative positions, and then call the relative position embedding matrix. Okay, that nn.embedding matrix. Embedding, it is not a matrix, it is a dictionary. Okay, lookup table. Call the lookup table for the value, and you will get an encoding. Just multiply your alpha value on the absolute position embedding and also relative position embedding, and then add those. That is how mixture works. And if you see mixture, right, you will understand actually how it works. You can see, right, we already saw sinusoidal. If you see, it was just zeros everywhere. Here it was just simple lines. And for relative, we didn't even see anything. It was just lines everywhere. But here, if you see, I'm also able to see the sinusoidal curve, and learnable position embedding. That kind of a structure is also seen, because I've almost provided each method 50%. So both are visible, right? So this is how relative position embedding and mixture absolute position embedding together will work. And yeah, 3 methods are done. Now we are coming on to the advanced methods, with the number 1 being rope. Still, I think we can keep rope for last, because rope is the most complex methods out of all of those we have seen. So we'll keep rope later. First we'll see ALiBi. Okay, So in ALiBi, what we are doing is in initialization, first we are initializing the linear projections, and then we are calculating the ALiBi slope. Okay, so first we are taking the M matrix, which is 1 to the number of heads, and the slope here is going to become 1 by 2 power 8 into the value here, and then divided by number of heads. Okay, we are registering this slope as buffer because this is not a learnable parameter. But when you initialize it as a torch tensor, right, it will become a learnable parameter part of the training. But we can't do that. So that is why we are making M as a buffer. In forward, what it will do is first, as usual, query key values are projected to its weight matrix, and then you have the reshape and all. So those are done, and then your attention score calculation is done. Right now, like I said, the third step is done. The fourth step is adding your ALiBi bias on the position difference between each token, and then apply the softmax and continue the same procedure. Now, how it is done? Now, adding the ALiBi bias, how it happens is first you are calculating the absolute value, negative absolute value of like -4, -3, -2, -1, that kind of a matrix which we already saw, right? That matrix is calculated here, okay, for the sequence length. And then what you'll do is we'll multiply the self.m value. We already saw that image, right? That is what is implemented here. Okay, this will actually create 1, 2, 3, 4, something like that, and then we are minusing subtracting it with the same value so that it will become negative at dimension 1. Okay, so we have here, you can see, right, minus of absolute. So it will basically generate a value known as -4, -3, -2, -1, something like that. And here we are computing the position difference actually. Okay, so one squeeze of 0 and then squeeze of 1, this will provide the difference in position at dimension 1 and 0. Now basically you are multiplying, this is your bias value, okay, and now you are multiplying it with self.m, which will scale the bias with the slope, and then you are adding it with the attention score. Okay, that's all. And there is a plot here, and if you see the graph, this will be a fun graph because, like I said, for each attention head you'll have a different kind of an output, right? Like at initial stages it won't be a lot different, but with a lot of training it will become a lot of different values. And here, if you see with ALiBi, yeah, it is very hard actually even to put it in here. You can see in heads, right? If I mask this, I didn't mask it. Here you can see the masked fill is not computed here. Okay, but at runtime, while we do the real time attention, right, what we'll do is we'll also mask it. So basically it will be masked here. Okay, on top of here everything will be blue, and this is how it will look like. Okay, just focus on this. Here, just consider this triangle is there, and that will be the position embedding value. First it will be close to 0, and then it will be going like close to negative values, because like I said, the upper values will become 0 with mask filling. This is how it works. Okay, ALiBi, it is very simple, but very efficient in nature. Now coming on to the most advanced method out of all of these, which is rope. So how does rope work? Here, what we need to do is, first we need that inverse frequency. Okay, the frequency at which you need to turn for your position encoding, the theta value and all. For that, inverse frequency is important. So that is calculated here, and then we are keeping that as buffer so that that isn't changed while training. And here we have the sequence length and all. Okay, in rotary position embedding, first what you'll do is you'll compute the sinusoidal value for each position by the inverse frequency. Okay, so each position you have, and then you'll multiply it with the inverse frequency. That is what is this einsum representing. Okay, so basically this is a matrix multiplication where we are saying this is the I here and this is the j here, and we are saying just multiply I and j together. Okay, now the sinusoidal input, for this sinusoidal input we'll calculate the sine and cos. Okay, so that is done. Here you can see we compute the sinusoidal input by multiplying it with the inverse frequencies, and this will provide you the rotation matrix, generates a matrix. And here what you will do is you will get the sine and cosine values of the sinusoidal input, and these will be concatenated together. The sine components will occupy the first half, and then cosine components in the second half. Okay, that is how here we have done. And here you can see the embedding is returned, right? But while attention, how it works is rotate half, just keep it because we'll use it in a different place. While attention, we are first calculating the required values here, and also we are initializing the rotary position embedding. Basically it's not a embedding tensor, so it is a generator. So we are initializing that generator for the head dimension and max sequence length. How it happens: first input x is obtained, the batch value, sequence length, everything is obtained, and then we are projecting it with the query key value, and then we are reshaping it. Next, the important step is to compute the position embedding. So now you have the positions, right? You are getting the sequence length. You will have 1 to n values or 0 to n values. For the 0 to n values, you are getting a rotary embedding matrix, not rotary embedding. Okay, that rotation embedding matrix is obtained. I told you, right? You will calculate a rotation embedding matrix, and then we'll apply it on top of the query and key, and that is what is happening here, right? First, if you remember, the cos of m theta into q plus rotate half, which will become negative, right? Negative of q into sine theta. Okay, similarly for it is cos k and plus sine k, minus sine k, sorry. The rotation matrix is already computed here, and that is what is here. Okay, so basically what you will do is we'll split the tensor into two halves, and the first negative half will be kept at first. Okay, and the positive half will be kept at second, so that when you multiply it, that formula which we said, right, will be applied. Okay, the rotation matrix is already there, but how you want to apply it on top of your query, the equation which we saw, right, that is how you need to compute it here. And then now you are applying your qk transpose, everything is normal. Okay, so if you see, aside from the rotation, right, all it is going to be similar to sine and cos. So the embedding generated, or else the attention which you see, should be similar to sinusoidal, right? Rope not there, rotary, yeah. Here you can see, right? See, still it is relative, right? See, there it was just some random lines which we didn't find any relation in it, but here it is relative, because if you see, when it goes towards the left, the values are getting slowly becoming towards negative, and also it is absolute in case of sine. So it is both relative and absolute. That is what is shown with this attention graph. Okay, so I hope you all like this video. I hope you all understood at least some basics towards different position embedding methods. In the next day, we are going to see on the different types of attentions. Here you can see the attentions is ready, where again here we are going to see visualize the attention methods, like how much attention each method will provide attention score and all. Okay, the attention graph, heat maps, everything will be seen in the next day. I hope you all like that video as well. If you all like this video, please hit the like button, share it with your friends, and also let me know your thoughts in the comment section. I'll see you all in the next video. Until then, happy learning.